Sure. Thank you, Jack. Appreciate it. Hi, everyone. Rob Morgenstern here, Unika Vaev, coming to you live from Dallas, Texas, where we're finally starting to cool down and getting some rain coming in from some tropical storm coming from Mexico. So the hot weather seems to be over. So now we're going to cool it off for Halloween, I guess, coming up. Thank you all for joining us. It's always a pleasure to talk to everyone about acoustics. It's one of my favorite subjects. And obviously, we have the CEU that we've been teaching for a few years now. Never got to give it live, in person before because of everything that's happened over the last few years, but hope to see you someday soon out in your territory. I am traveling again. All that's coming up again. So hopefully we'll get back to some normalcy soon. So looks like we have a few people here ready. We'll just get started and people can come in as they get here. You may be an acoustician on the line. I hope not. You may be. I'm definitely not an acoustician. I'm the VP of Sales for Unika Vaev. But there's certain things about acoustics that I've learned over the years. We're part of what's called the NCAC, the National Council of Acoustical Consultants. We're a sponsor of that group. And we've learned a lot from them, and it's helped us put together two different CEUs. One is an older one that I've shelved for now. And the one you're going to see today is called Acoustical Concepts 2. And it's a great CEU. It gets pretty technical, and I wouldn't say you have to memorize all this stuff, but it's certainly going to help in your understanding of especially speech intelligibility inside interior environments. That's what we do at Unika Vaev. That's what Han does in our partnership. And it's just good to know a little bit of the background about acoustics before we start filling up rooms with all sorts of acoustic material and hoping for the best. So what I'm going to do is I'm going to turn off my camera because I tend to get distracted by myself. So I don't want to do that. But what you can see here is Acoustical Concepts 2, and we'll get started. This will take about an hour. I'll try to talk a little bit faster if I can. If there's any questions at all, I think there's a way that you can write them in, or you can put them in a chat box, and we can address some questions at the end. Keeping in mind, I'm not an acoustical consultant, but I do know many of them. So if I can't answer your question, I can certainly get an answer for you. All right, so Acoustical Concepts 2. Here is the AIA information and the IDCEC information. If you are an architect or an interior designer and you want to have credit for this, all we'll need is your name and association number, and then we'll need that relatively quickly. I'd like to have it by tomorrow so I can get everyone their points that are necessary. If you don't need points, then just sit back and relax, grab a tub of popcorn, and away we go. Now let's see how to. Okay. All right, so introduction. Let's talk about acoustics, all right? We're going to review some concepts. Many of you probably did not see Acoustical Concepts 1. That's okay. We're going to review concepts from Acoustical Concepts 1. We're going to talk about speech intelligibility. That's what we do best. That's what Han does best. And it's really what's necessary when we talk about acoustics, as far as I'm concerned. We'll discuss an acoustical palette of absorption and diffusion, and then we'll sum it all up, okay? All right, let's review some sound, noise, and acoustical remedies. What is sound? If you can hear me talking, you understand what sound is. I mean, you can hear me, so you know that sound is working. But sound requires mechanical energy. It doesn't become sound unless it has mechanical energy attached to it. You require a medium of transmission. So like water, metal, wood, air. You need that in order for sound to be sound. You also need receptors. In this case, we're using our ears to pick up the sound waves that are coming at us. And it possesses certain characteristics, which we'll get into. Now, if I was right in front of you, when I do this in person, I usually have a tuning fork. And anyone out there who's a musician knows that you strike this on a block of wood or a table or something, and the tines start vibrating and put off a sound, all right? What's happening with this? So basically, when you strike the tines on a piece of wood, for instance, tines start vibrating back and forth very, very quickly. And there's energy coming off of that from that interaction. And as the tines are vibrating, it's affecting and going out from the tines, affecting all the air molecules that are all around us that are invisible, but they're there because we're breathing. When that energy goes out, it hits the air molecules. They start bumping into each other. Think of like dominoes in a line. You hit one and then they all start moving. It passes the energy on to the next air molecule. Once the energy is passed on, then the air molecule goes back to its original state. So it kind of swings forward and then swings back. When it swings forward, it's called compression. When it swings back to its original position, it's called rarefactions. Okay. Now, how fast does sound travel? Well, basically, it depends on the medium that the sound waves are going through. If it's air, sound will move at about 1,125 feet per second. That's very, very fast. But if it's salt water, it goes about 5,000 feet per second. And if it's something like steel, sound waves will move at over 16,000 feet per second, which is really interesting. And the reason that happens is because the molecules are much more dense in steel than they are in liquid, than they are in a gas like air. So the closer the molecules, the farther the sound will travel and the faster the sound will travel. But we're typically dealing with air. But you know, when you're talking about acoustics in buildings, you have a lot of wood, metal, and those types of things, and that's taking the sound forward as well. So once those sound waves actually reach our ears, the waves go to our brain through our ear canal, and our brain recognizes what you're hearing as a sound. Okay, and keep in mind that we as humans, we can hear faster than we see, taste, smell, or feel. Once a sound reaches your ear, your brain recognizes it in about 50 milliseconds. That's 0.05 seconds. And then realize it takes 4 times as long for your brain to understand light or to recognize something that you touch. So we're probably developed that way because way back in the old days when we lived in caves and it was dark, there was no electricity, hearing was the primary defense mechanism. Because our ears, we need to hear things at night when there's no lights anywhere. We need to hear that bear sneaking up or whatever, a saber-toothed tiger sneaking up on us. So our ears are extremely sensitive, and when they're working properly, we can hear things very, very quickly. Now, how do we know when a sound is coming from the left or from the right or from straight ahead of us? Well, once we hear a sound, our brain tells us from which direction the sound came from. It's called the law of the first wave front. If a sound originates like the helicopter showing on the left, then you're going to hear it in your left ear microseconds before you hear it in your right ear. And that's because our big old head's blocking the wave. And so we know it's coming from the left, but it gets to our right ear very, very quickly. So you're not hearing an echo. You're just hearing you can't even hear the delay, most likely in most cases. You'll just know the sound is coming from the left. And the sound you hear first on the left or right still sounds like that one sound because of something called the Haas effect. The Haas effect basically says that anything you hear in less than 40 milliseconds, you're going to hear as one single sound. If it's longer than 40 microseconds, then it's going to seem like an echo because there's too much of a delay. So this has consequence in room geometry, so we'll discuss that a little bit more. And here are some characteristics that we'll discuss. Frequency, you might have heard of some of these terms. Wavelength, pressure or loudness, and resonance, which is induced vibration. Frequency, which we'll talk about first, it just means the number of back and forth vibrations for that wave that's coming out from where the interaction took place. Remember the tuning fork, and the energy coming off of the tuning fork is creating these waves that look something like this. And there are low frequency waves. Those lower sounds tend to be longer waves, larger waves. There's more energy in them. And there's what they call mid and high frequency rays. Rays are like waves, but they're much, much smaller because those very high frequencies, kind of like a bird chirping, they're not as strong as what you'd hear like someone driving their car down the road and you hear the bass coming out of the car when they're blasting their music. Those rays are kind of like the white water that washes up on the beach, and the waves are like the ocean waves, much more powerful and are very much more difficult to control. And we'll talk about that. Now, when we talk, and there's our language on this chart that you see in front of you, our language exists from about 125 hertz to 5,000 hertz, okay? From 500 hertz to 4,000 hertz is the most important for speech. So consonants, if you think of consonants, the sounds that a consonant make are about 2,000 to 5,000 hertz. So very, very, the higher you go up, the higher frequency. Again, think bird chirping, or think of the sound S or something like that as a very high frequency sound. And the vowels, A, E, I, O, and U, sometimes Y, are in the 500 hertz to 2000 range. But we all have a fundamental frequency. Fundamental frequency is the lowest frequency. For a male voice, it's about 125 hertz. It's the lowest that the typical male voice can go. Females about 200 hertz, and children are about 300 hertz. And there's a reason why I talk about this. And when you're trying to control speech in an interior environment, you need to focus on products that can absorb or block those specific frequencies. You don't have to worry so much about the low end frequencies or extremely high end when we're talking about speech, and you'll understand that as we go through this. Okay. Now, given that sound travels 1125 feet per second, the length of a sound wave, for instance, having a frequency of 1000 or 1000 hertz, that wave is about 1.125 feet long. So it's kind of big, but the wavelength of a 250 hertz sound is 4.5 feet. And so you have a 4000 hertz sound, very high frequency. It's only about 3 inches. So, think about that when you have, say, absorbing panels on the wall or on the ceiling, and you're trying to absorb a wavelength that's about 4.5 feet long. It's not as easy to do with a 2-inch piece of material that's up on the wall, but you can easily absorb the 4000 hertz because it's only a 3-inch thick wave coming at you. So consider that these wavelengths can be very long, very powerful, and can be a bit more difficult to control. And when you can't control them, that's typically what can cause reverberations or even echoes in our interior spaces. And that's what we're trying to get rid of when we're trying to improve speech intelligibility. And we'll discuss this more. So let's talk about strength of sound. So at every spot in the room where there's a sound source, so consider the speaker, for instance, there's a particular sound pressure level. It's basically an amount of energy over a unit area. It's called pascals. Human hearing requires 20 micropascals of sound pressure in order to make our eardrum vibrate. And as you'll see later in this, sound pressure levels are higher closer to the sound source. So the closer you get to that speaker, the louder it's going to be. There's going to be more pressure coming at you. But consider that when something is 20 micropascals in pressure, and that's the minimum, that's 0 decibels. So we'll talk about the decibel scale. 0 decibels, we can still kind of hear. It just starts making our eardrum wake up and start working at that point. So sound and the strength of sound. Sound has an energy level and a direction, and its measurement, I'd say it's in watts per square meter. Again, you don't have to worry about all these terms, but it's in watts per square meter. But someone like a baby's cry, tones of the same intensity, but of different frequencies, can be perceived as louder. And this is a consequence of resonance that occurs in the ear canal. So there are certain sounds and certain frequency levels, maybe higher pitched, that will make our inner eardrum vibrate more so than a lower frequency sound. So we perceive it as being louder. So again, it might be the same strength that this baby is either laughing or screaming at you, but we're going to hear it as being louder because, as you can see on the bottom there, he's pretty serious about his crying right there. So here's that decibel level scale that I told you about. It goes from 0 and on up as high as you want to get, but fireworks are about 125, 130 decibels. It's amount of pressure. And then a living room is typically around 40 decibels. To understand that, I took this from our Dallas Morning News, and this is what they have in our restaurant section. It tells you how loud or quiet a restaurant's going to be. So if you want to see this chart before you go, and if you don't like loud environments, you're not going to go to certain restaurants. So it's kind of cool. But you can see that below 60, it may be too quiet, and 60 to 69, normal conversation and up. But if a restaurant's listed at 86 decibels and over, you're not going to have any conversations. And I know you've all been to restaurants that are like that, where you pretty much have to text each other because you can't hear each other talking. Some people like that. I don't. I'd probably be in the 60 to 69 so I can actually talk to people. But it's up to you. But that's just a good way to understand it. And that kind of puts in some kind of perspective of how sound decibels work. OSHA did a study on this, and they wanted to figure out how long you can be in a certain environment at what decibel level. And they used what's called an A-weighted decibel. All that means is they filter out the low frequencies and the high frequencies that we can't hear anyway, because we can't hear all the way down to 0 hertz. It's just, we're not built for that. So it's almost like an average, but it's just filtering out the highs and the lows. But what they found out was that you can be in an interior environment at about 90 decibels A-weighted for 8 hours, and you're not going to damage your hearing. But if you simply raise from 90 to 100, it's only 10 decibels, but every 10 decibels up, it means you're doubling the strength of the sound. So at 100 decibels, you can only be in that particular situation for 2 hours before you start getting hearing damage. And hearing damage is tough to reverse. And we all, as we get younger with age, we all start having some issues with our hearing. And there are ways to get some of it back through, electronics, but it's not very pleasant. But just know that we need to be talking to people about how important sound is and the loudness of the sound, and how if you lose your hearing, it's not going to come back too easily. So keep that in mind with OSHA. Now with the sound intensity, this talks to you about how does the distance affect sound. So one easy way to understand how distance affects sound's intensity is this. Say that you're up against a speaker and it's putting about 60 decibels out, not extremely loud. It's about like me talking right now. And you're 2 feet away from the speaker. If you double the distance to 4 feet away, every single time the decibel level from that source will drop 6 decibels. You move again then to 8 feet away, so you're doubling the distance. You'll have another 6 decibel drop in intensity. This is important if you're designing something where there's some heavy machinery or there's some loud sound source that you need to have people work at a certain distance from it so it'll keep the noise down. You can kind of use something like this and understand how far away you have to be from the sound source, because as you get farther away from it, it attenuates in the air and just kind of goes out in all directions. It becomes less powerful when you go out from it. But keep in mind that distance alone, it doesn't stop sound transmission. It still goes. And if you're listening to a source in a room, say with the door closed, you're dealing also with reverberations off the walls, the ceilings, and the floors, and that can make the room louder. And we'll discuss that coming up, and you'll see what that means. So let's talk about sound pressure and decibel levels. So if you have one rocket ship and you're measuring that at 90 decibels, it's pretty loud. If you add a second rocket ship that's also at 90 decibels, it doesn't become 180 decibels. It's basically, because of logarithmics, it becomes 93 decibels. So a little bit louder, probably not so noticeable, but it will get louder. But if you have to double the sound, again, you're adding 10 decibels, you need to have 10 rocket ships. And that's what'll make it go up to 100 decibels. I always talk about restaurants. I used to work in one, so I totally understand them, and you've all eaten in them most likely. People are kind of like this too. When you're sitting in the restaurant and say there's just a few people sitting in there, and then another table comes in, then another. This should work this way, but we're competitive and we raise our voices to be heard over the people that are next to us. And thereby you're basically raising the power of the sound source. You're no longer at 60. You might have raised up to 70 decibels because you start shouting. This is known as the Lombard effect. And it's often found in restaurants, which is why I say that. And it just means that everyone starts shouting to be heard over the table next to us, and it gets really, really loud in there. And as people start filtering out, if you still stayed at that volume, people will be staring at you because you're really loud. But before, they didn't notice that was going on because there were so many people. When you get that loud and start shouting, it includes not only the loudness, but also the pitch, the rate, the duration of syllables. Everything changes, and it makes it, again, more difficult to hear. Now, resonance we talked about when we're talking about the inner ear and resonance. Resonance or induced vibrations occurs when the frequency of a disturbing sound equals the natural frequency of an object. So for instance, if I had 2 tuning forks here, I strike the first one, they're both in the key of A, and you have a certain apparatus that they're set up in. You don't even have to strike the second one. It'll pick up on those vibrations that are coming from the first, and it'll begin moving on its own because it's affected by the waves that are hitting it. Building materials like drywall, they actually have a resonant frequency, and certain frequencies make the drywall vibrate. You can't see it, but it's vibrating, and it adds sound to the room because there is a sound coming from that vibration. So when you listen to music in a room, you're actually hearing the room sound because of all the building materials in the room, and they all have a sound of their own when they're disturbed by their resonant frequency. So it's very different when you're listening through headphones. In fact, one goal of a music room, if you're designing a music room, is to make the room sound go away and to sound more like you're listening through headphones. It's not impossible to do. It can be done with the right materials, but you want to get rid of that room sound because it's extra energy in the room that you don't need. You just want to hear the source. Okay, so let's talk about noise. We always talk about noise as sound's evil twin, but what is noise? It's unwanted sound, and there are adverse implications. All right, noise can also be considered as any sound that interferes with the detection of a target sound. So in some instances, speech or a mixture of speech sounds may disrupt a listener's ability to process targeted speech. You can't hear what that person is saying because there's all this other noise in the background. Okay, these are the adverse implications. You got physiological, psychological, behavioral, cognitive. Let's talk about psychological. Basically, increased stress and job fatigue results from noise and may lead to more work time lost because you just can't, it's just too much and you can't handle it unconsciously. You may feel tired when you leave the workplace because you're in a very noisy place and you don't really know why you're tired. It's because your brain is constantly processing all that noise. And a decreased cognitive ability and lost concentration is going to impair your productivity. And it's been studied many, many times. If you're sitting in a quiet area and all of a sudden there's a loud crash, it's going to take you away from what you're doing to that loud crash. And if you're like me, you try to get back to what you were doing and you've lost your train of thought, then you got to spend 10 minutes to try to figure out what you were doing. And so sounds can have that effect on you too, and that's when they become a noise. But both factors should be recognized by employers as factors in considering their acoustical work environment. And it's important to know the difference, all right? When we talk about room acoustics or sound transmission, this is often confused, but let me explain it this way. When you create an insulating barrier, like a wall, that prevents sound from invading the space, it's like you don't want that truck sound coming into the conference room, so you have a very high, say, STC wall that's going to block all the sound coming in there. That just means that the noise that's generated in the room from people talking or whatever is going to have a hard time getting out, because if it can't get in from the outside, the noise is not going to go out because it can't get through that building material. So then you're dealing with all that energy that's trapped in the space, and if you're in a room that's pretty typical from what I see is glass all around you, or drywall, or polished concrete, or any of that stuff, you're going to have all this extra energy that can't get away because those are not absorbing materials, and they're going to bounce the sounds right back at your ears, and that's why it sounds very reverberant or some sort of echoes, because it's not able to go anywhere. It just kind of moves around in the space until it dies away, and that causes a lot of problems. And most spaces that you have require making a choice in room acoustics. Is the goal to enhance reflected or reverberant sounds? If it's yes, you're probably talking about a theater, music performance spaces like that. Or is the goal to control noise by minimizing reverberant sound energy? Offices, libraries, hospitals, and that type of thing. That's why it's always important, and I always ask this question, what are you using the room for before we add or take away any type of a treatment? If you just say, I have this room and I have no idea what it's being used for, you might have too much material, too much absorption, where the music sounds dead, or you might have too little where it's not doing enough to help and people can't communicate properly because of all of the polished concrete and drywall and glass and such. So it's always important to know what type of room you're planning for. And that's where we get to the idea of speech intelligibility. It's the measure of the capability of being understood, all right? Can you hear and understand what I'm saying, even with the noise that's present in the room? Right, that's what speech intelligibility is. Can you hear me clearly? And remember, the products that absorb sound, like the panels and tiles and all of that, they work to improve speech intelligibility. That's what they do. That's what their goal is. Now, we talked about this a little earlier about room sound and how it can make a source sound louder. Here's an example, real world example. Say you have two people in a room. The person on the left is talking, and she's talking with about 68 decibels, which is pretty normal. you hear that 68 decibels, okay? You hear that as part of the sound. But what you're also hearing in this example is what's called the primary reflection and the secondary reflection. That sound that's coming out of her mouth is not only going to your ears, it's also hitting the walls, it's also hitting the ceiling and floors, and it happens very, very quickly. And in that 0.4 seconds that we talked about, okay, under 0.4 seconds, it's not going to sound like an echo, but you are getting extra energy because the waves are hitting, say, the wall and then coming to your ear. All right, that's at 65 decibels because some of the energy was lost when it hit that building material. And then the second, what you're seeing is 62 decibels is if it hit the ceiling first, then the wall, and then your ear, it loses a little bit more energy. But all that combined together, like those rocket ships, adds up to 70.5 decibels. So it's actually louder in the room than what's coming out of the person's mouth because of the extra energy that's created and stays in the room because it can't get out or it's not absorbed. And that can cause a lot of problems if you have a lot of people talking like this and then it just kind of raises up and it makes speech less intelligible. And there are ways to fix that. There's something called the speech transmission index that measures this. It goes from bad to excellent, as you see on the screen. And acoustical consultants can help with this type of thing. But if you have a bad STI, that means the intelligibility of the words that you're hearing, you're only understanding from 0 to 67% of what's coming out of my mouth, for instance. That would be bad because you're going to miss a lot of information. It could be excellent at an STI value of 0.75 to 1. That means you're understanding 94 to 96% of the words that I'm saying. But keep in mind though, bad is not always bad, excellent's not always excellent. And what I mean by that is if you are, the STI, speech transmission index, among team members within a shared space should be greater than 0.5, all right? People outside of the team zone should avoid disturbance from the team speaker. So theirs should be less than 0.2. So sometimes you want bad STI because you don't want people way across the hall hearing and understanding everything that you're saying. And sometimes you want excellent because you want the people that are near to you in your team to hear and understand what you're saying. So it's, just keep that in mind, bad is not always bad and good is not always good, okay? This gets us to speech privacy. It's almost the opposite of speech intelligibility, but speech privacy is the inability of an unintentional listener to understand the substance of another person's conversation. It's not necessarily that you can't hear the conversation at all, but there is a level of speech privacy that allows for that, where you can't even hear the people around you. There are 3 standards of speech privacy, especially in an office: confidential privacy, normal privacy, and transitional privacy. Normal is the minimum standard. And that's where some of the sentences are intelligible, but the volume of the conversation is not such that it's going to distract you, and it's not going to be informative. So you might hear voices coming through the walls from the person that has the office next to you, but you can't really make out what they're saying because it's kind of mumbled a bit. And so therefore it's not really, it might be a little bit disturbing, but it's not so disturbing because you can hear every single word that they're saying. So the speech privacy in that case is pretty normal, and that's usually technically good. But there are cases where you don't want anything that's said in that office to get out of that office. And that's where you'd want confidential privacy. And we see that in a lot of, say, like government buildings and such, where they just can't hear you. You have to use barrier technology, building materials, to keep that speech from traveling through the walls, for instance. And products that block, we call them blocking the sound. That's the barrier technology that I'm talking about. It's not absorbing panels. It's blocking technology, barrier technology. So let's go back to speech intelligibility. There are some primary factors and other factors and such. The most important part of speech intelligibility is something called reverberation time. Reverberation time is just basically excess reverberation time. They call it RT60. It's the primary cause of amplitude and frequency distortion, and it affects speech intelligibility. It's how long the energy that's created in the room stays in the room. And one common mistake that people make, and I see this question come across now and then: what's the NRC of the room going to be once your stuff's in there? Well, NRC is a rating for products. Rooms don't have NRC ratings. Rooms have reverberation times that are affected by the building materials and their NRC ratings within the room. So acousticians perform what's called a T60 test to find out how reverberant a room is, and then they make recommendations from there, suggesting certain products at certain NRC levels to help absorb that extra energy. But what is reverberation? You know, a lot of people say echo, and it's kind of a reverberation. But reverberation is basically just extra sound energy that's in the room. They're caused by sound waves bouncing off the walls, the ceiling, the floors. Hard surfaces can cause reverberation because hard surfaces don't absorb sound well, obviously. And whether the aim is to make sound beautiful, to make speech intelligible, or to simply reduce the noise levels, getting the correct amount of reverberation in a space is critical to the design of most rooms. Not only do you hear the direct sound, like we talked about, but you also hear the primary reflection, secondary reflection, tertiary, and all that adds noise to the room, and that's all reverberation. So how long does the sound remain in the room? That's the reverberation time. That's that T60 or RT60 test that an acoustician will test out. So what they do is when they measure how long it takes for a sound to decay by 60 decibels. Why 60 decibels? Well, that's when 98% of the strength of the sound is gone once it's been reduced by 60 decibels. How long it takes to decay at the different frequencies, it lets you know what the T60 time is. So in rooms where speech is a main concern, we really look at three frequencies: 500 hertz, 1000, and 2000 hertz. And those are all very important speech frequencies. And they look at the reverb times at those what are called mid frequencies. What you're seeing here is an actual chart from a project that we worked on that showed when they went in and did their RT60 test, they showed at each of these different frequencies how long each frequency stuck around once the sound source was cut off. So if we're talking about 500, that sound lasted 1 second, the extra sound. At 1000, it lasted 1 second. At 2000, it lasted 0.7 seconds. Well, you may say, well, that's not very long, 1 second. I mean, we can deal with that. But in reality, 1 second, because sound travels so far, 1125 feet per second, that's not good for certain types of rooms. How do we know? Well, we look to LEED, and LEED guides us and tells us what the T60 time should be. So for office buildings, if that is the conference room, in which it was, we should have a T60 time of about 0.6 seconds. So more or less, you're looking at those three frequencies, and you saw there 1, 1, and 0.7. We're trying to get that down as close to 0.6 seconds as possible. And when we do that, we know that a lot of the reverberation is going to be gone. Just in that little bit amount of time, a lot happens. But closed noise-sensitive spaces, I call them, like meeting rooms, conference rooms, private offices, they should have a T60 time of less than 0.6. And open offices should be less than 0.8. All right, that's what LEED says, so we follow along with that. And keep in mind, when there's less reverberant sound in the space because you've absorbed some of it, other sounds occurring in the space and disturbances originating outside of the space, you may be able to hear them a little bit better. You may be surprised by that because that extra energy was covering up some of the sounds, but now not so much because you got rid of the extra energy. And if your wall's a little thin, then you might have a problem with hearing a little bit more from what's coming out of the room next to you. But again, you can take care of that through building materials, and that's why it's a balancing act, this whole thing. So let's talk about the ABCDs of acoustical remedies. This is really, really good to remember and to understand because it helps you pick the right product for the right problem. Okay, absorption. A is for absorption. Products that absorb improve speech intelligibility. Products that block improve speech privacy. C is for cover, and covering enhances speech privacy. That's like sound masking. When you're in a big open office, it's open, so there's nothing to block the sound. There's no walls there, so it's a one big space. So you add extra energy to the room to cover up some of the sounds, which I'll get to. And D is for diffusion. Diffusion scatters sound energy. It makes it sound fuller. It's often used in like recording studios, home theaters, music rooms, and that type of thing, to just make it sound more full of the room, of sound in the room. So these are some wall absorbers. You might recognize some of these, but These would be your typical wall tiles that improve speech intelligibility. They act like sponges and they absorb the extra energy that's in the room, and they look really good at the same time. And then these are ceiling absorbers. This just happens to be one that magnetizes to this grid in this case. Works the same way. Since the ceiling is a surface, you're going to have sound bouncing up there too, so you might want to get some stuff on the ceiling to absorb some of those waves, just like a sponge absorbs water, obviously. Screens, they're both A and B, absorbing and blocking in some cases, not all cases. But to be effective, screens should not permit sound transmission through them as much as possible. They should also have an absorptive facing to prevent reflection back to the sound source. All right, you want to capture some of that energy so it's not bouncing right back at you. And they should be large enough so that the mid-frequency sound doesn't easily wash around them. Some of these waves are so big, they just get up to the screen and they just go right over it because it's such a big wave. To effectively block sound or noise, you really have to consider the frequency, the amplitude of the offending sounds. I mean, I'm not trying to make this difficult, but there's a lot to, you can't just put a piece of material between you and your work partner. I think that'll solve all the problems. There's some ways that you can do this properly that is really going to help both of you. Mobile quiet rooms, some of you might have these in your spaces. It's absorbing on the inside, it's blocking on the outside. Most quiet rooms provide sound insulation, and the efficacy is best measured in the reduction of decibels. All right, so you've seen this in a lot of places. That sound masking, like I was talking about, it helps increase speech privacy by masking conversational noise. The sound masking puts out this sound that carries no information. One of the most widely known is something called white noise, but there's so many different types of sound masking. But white noise, you've probably heard of. It's a sound that has equal sound energy in each of the frequencies. So it doesn't grab your attention so much, it's just a sound. To cover up someone talking that may be 75 feet away from you, you're hearing the sound coming out of a speaker that's right over your head, and it covers up the person that's way across the room. But sound masking is not appropriate for spaces where higher STI is critical. For instance, they wouldn't be placed in a conference room necessarily because you want to hear the person talking in there. Too much sound masking is not a good thing. It's kind of like just too much perfume. Sometimes you get unwanted results from that. And then D is for the diffusion. Diffusion scatters sound energy. It's kind of like you take a glass and you throw it on the ground and it scatters in a million pieces. That's what it does when the sound waves hit the diffuser. They scatter in a million pieces and travel all around the room. The same amount of energy, but it's spreading out the sound waves so it sounds more full. You often have them in, like I said, home theaters, and they're usually placed behind you. So when the speakers come at you and they hit the diffusers behind you, they scatter in 1,000 different ways. And when you close your eyes, you shouldn't be able to tell where the sound is coming from. And that's what really diffusers do. I have never seen them in an office necessarily or in a conference room, but maybe they're out there somewhere. But that's primarily what they're used for, especially when we're using music or live stage productions or that type of thing. But it's very important. And diffusion and sound redirection, they've been around for many, many years. Santo Spirito was completed in 1487. And they knew this and they understood this back then, how the sound redirection or diffusion works. The round columns and the other reflective convex structures, they make very good scattering surfaces. That's not true for concave, which we'll talk about. But in classic architecture, scattering surfaces such as columns, relief ornamentation, statuary, coffered ceilings, they're all an integral part of acoustic design. But keep in mind, it doesn't work well with low frequency sounds, or very low bassy sounds, because it's just too powerful of a wave and just goes right past it. But it's for the mids and the highs, and it really, really helps to spread that energy around the room. So we talked about that reverberation time. There's some other factors like background noise, signal to noise ratio, room geometry, all important. Signal to noise ratio is used in a lot of classroom applications where you want the speaker, the professor, to have a certain decibel level higher than any of the noise that's in the room, maybe coming from the HVAC, maybe coming from someone mowing the lawns outside of the building. So, you want to be at a certain level over the noise, and again, acoustical consultants can help you figure out what that signal to noise ratio should be in your case. And critical distance is basically the distance from the sound source where the direct and reverberant sound energies become equal. And the more reverberant the space, the closer you have to be to the sound source to hear that sound source properly, obviously. Because, you know, consider the people sitting in the back of the classroom with an STI of 0.5. Well, they're only at best receiving half of their education because you can't understand, you know, a lot of the words that are being said. And if you're all the way in the back and say that person in the front is speaking at 70 decibels, 32 feet away, you're at 43 decibels because of what I explained. So that and you're hearing the speaker unless there's a microphone or something, but you're hearing the sound energy you want to hear much at a lower volume because you're farther away from it. Beyond that critical distance, the level of the direct voice gets quieter, but the level of the reverb, believe it or not, stays the same. The level of the reverberation will remain constant throughout that room because it's going so many different places. But the voice level, as we learned, loses energy every doubling of the distance. And room geometry is a big deal too. I mean, that can make rooms sound good or bad. There's something called flutter echo, which I've experienced. I have to, if I was there in person, I could really show you what it means, but it's energy trapped between two parallel surfaces. It's sound bouncing back and forth from wall to wall. It's really annoying. The acoustical effect is something like standing between two mirrors and seeing infinite images. Absorption can help, diffusion can help, and canting of the walls can help as well. Those flutter echoes can be nasty in long conference rooms with lots of parallel walls. So you want to make sure that you have something to get rid of that or scatter that energy around or make it go a different way instead of just bouncing back and forth. This gets a little complicated, but I'll get through this quickly with you. But another way that room geometry plays a role with speech intelligibility is when it comes to what's called standing waves. This really has to do with low frequency pressures, which are very large and don't fit in the room. There are pressure areas that are created, and you have them at the walls, in the middle of the room, and in the middle of the room when the room's too small for the low frequency energy. So if you have an 18-foot long room and you have a 30 hertz wave sound, which is pretty low, a 30 hertz wave is better than 37 feet long. So how's a 37-foot long wave going to fit an 18-foot long room? It won't. It'll go out from the source, form about the first half of the wave, and then three things happen. Some of the remainder of the wave will go through the wall, some will accumulate at the wall, some will reflect off the wall and head back to the source. It's basically going to do battle with the next wave that's coming out. Picture two ocean waves going right at each other, and they hit in the middle and go straight up. And so you know that's a standing wave. It gets stronger and taller right in the center. So if that's happening with sound, it might actually sound louder in certain parts of the room than it does in other parts because that's where the waves are hitting. It's pretty cool actually when you experience it. You can avoid those standing waves. You just have to calculate the room modes. It's as easy as that. Room modes are pressure areas in the room where sound energy doesn't fit within the physical dimensions, okay? There's a few different types: axial, tangential, oblique. Axial modes show you the pressure areas that occur between two parallel surfaces. Sidewall to sidewall, front wall to rear wall, floor to ceiling. And the others do more walls, basically more surfaces. But axial modes are always the strongest amount of pressure. And the way that you can avoid them is when you design your room ratio a certain way. For instance, the ratio could look like 1 to 1.4 to 1.9. What does that mean? Height, width, length. So a room with a ceiling height of 10 feet should be 14 feet wide, should be 19 feet long. This will help the modal distribution. The worst room is a perfect cube. So if you have a 10 by 10 by 10 room, it's going to sound awful in there at certain frequencies because you're going to have the offending frequency at each part of the room. It's going to resonate at the same frequency. It's just going to sound terrible. So if you're designing spaces, there's many, you can look up room modes on Google or whatever and see there's all different types of modes that you can design and ratios that you can use to make the rooms sound better so you don't have pressure areas in certain areas of the room. Okay. Hope you're all still with me. We're not too much further here. Room geometry, we also talk about convex walls like columns. They're good at redirecting sound, as we learned. Concave walls like this are rarely a good thing, and they focus sound rather than distribute sound. So I've seen some like classrooms in the round. It's terrible for the professor, especially if they're in the middle of the room and walking around, that their sound is just coming right back. All the sound generated is coming right back to them at every single piece if you just have bare walls. There are ways to fix that with diffusers to make the waves scatter. But there's something called the Statuary Hall in the US Capitol building, if you've ever been there. It's called the Whispering Gallery, in that a speaker's voice, when reflected downward off the ceiling, can be heard well across the room, even if a person's whispering. It's crazy. And it's because of this geometry. It just goes up and then comes right back down to the center. So we want to avoid that as much as possible. Acoustic spaces can be categorized into 3 broad applications, right? Sound production, sound reproduction, and the intelligibility of speech. And each type requires its own set of acoustic solutions. So here's that, we talked about reflection. That's just when the sound hits the bare wall, for instance, and reflects off at an angle. If you have some absorption on the wall, some of the energy will be absorbed into that material that's on the wall, for instance. And so you're still going to get the same angle coming off. When the wave hits it, it's going to come off at that angle. It's going to be less powerful, so it's not going to last as long. And then there's that diffusion, which scatters the sound energy into all parts of the room. You may have heard of Wallace Sabine. He's basically the founder of modern acoustics. He was the one that figured out what absorption is in the 1800s, how it works, what it means. Basically, the process of decay, of turning sound energy into heat energy is what's happening there, and he called that absorption. And there's different ways of measuring it, but there's a sound absorption coefficient, which is called alpha, how much sound is absorbed by a material. He also has come up with something called a Sabine, because of his name. But a Sabine is basically 1 square foot of an absorbing material that has an alpha of 1. And when something has an alpha of 1, it means it's a perfect absorber for those frequencies that you're trying to absorb. Okay. And just think of it as like 1 square foot of open window on a wall. If you have 1 Sabine, you have a window that's 1 square foot, and it's open because what's a perfect absorber? An open window, because the sound's going to go out and not bounce back, and it's going to go somewhere else. So if someone tells you, if an acoustician tells you you need 500 Sabines in this room, in effect, he's saying you need 500 square feet of open window. And that's more or less the same idea, where all the sound's going to go out. But the problem with open windows is in the winter, in some places, and also sounds out there are going to come in very easily. So that's why you have to get products that mimic an open window and not an actual open window for this stuff. But it does work. Absorption coefficients, they're determined by placing absorbent material in a very reflective room, like it's called a reverberation chamber, and measuring the change in the reverberation time at different sound frequencies. Okay, that's basically how they do this thing, how they do that. And with diffusion, it's the same type. It's called a scattering coefficient. Again, you don't need to, it's just interesting to note. You see that scattering and diffusers work better at the higher frequency sounds than they do at the lower frequency sounds. You've probably heard of NRC. You may not have heard of SAA. NRC is the average of, it's basically an average of how absorptive a material is at 4 frequencies, 250, 500, 1000, and 2000, rounded to the nearest 0.05. So sound absorption average, SAA, is a new number rating. It basically looks at 12 different frequencies, so you can get a little bit more complex on there and find out a little bit more about what that sound is actually doing at a few different frequencies. So you may see both NRC and SAA. You can figure out how much the reverberation time is in a room with this formula. Or if you know the time goal, you want the reverberation time to be 0.6, you know the volume of the room that you're working with, you have to figure out how much absorptive surface you need, and that's all part of this formula. And we use this, but acousticians use a lot more than this. But this will give us a good idea of how much material is needed in a space to take care of that reverberation. If you don't know where to start, I always suggest looking at GSA's white paper called Sound Matters. That's been out for a few years. It gives you the acoustical requirements for federal government buildings and certain spaces. So if you look at, say, like, I don't know, the open plan workspace with normal speech privacy, it tells you that a good idea would be to provide absorption of an NRC of 0.9 on 100% of the ceiling, and absorption of 0.8 on a minimum of 25% of the walls, and some other information there too. So if you don't know where to start, they're good guidelines to go by. There are different types of absorbers: porous, perforated, membrane, resonators. Porous absorbers is probably what you're most familiar with. It's basically made up of a fabric, and when the sound waves hits the fabric, the fibers start vibrating and rubbing against each other, turning the sound energy into heat energy. And you can't feel the heat coming off there; it's indetectable. But that's what happens with absorption, and energy is also lost due to the vibrations of the absorbent material. You can make an absorbing panel work better if you get it off of the wall. If you're putting these things directly onto the wall with, say, glue or something, and a lot of people do, put it directly on there, the sound is not going to work on the back of the panel. Think about it. I mean, these sound waves are traveling all around the room through the air. If they get a chance to access the back of the panel, it's going to get absorbed back there too. So you leave that space about 2 inches or so with standoffs. You're going to typically get these absorbers to work better because they're being absorbers for the back. Now that doesn't work with the low frequency sounds, but there is something else that works for them. There's also baffles, clouds, Lapendaries. You're probably familiar with these. Those absorbing material that's up in the ceiling in very large rooms. All right, it's another thing that you can do. And with baffles, there's a general rule of thumb for baffles, not just how it looks, but if you want it to work a certain way. We generally say if a baffle, say it's 48-inch wide, 12 inches deep, then I would go 12 inches to the next baffle. So 12 inches on center to the next baffle. And that's going to get you a really good performing system. Again, the sound waves are being absorbed. But if you get the baffles too far apart, it's not going to work as well. And if you get them too close together, it will work better, but it's going to cost you a lot more because you have more material and it may be unnecessary. So that's typically the rule of thumb that we look at, is the spacing is the depth of the baffle. There's perforated panels too. You've seen these micro perf panels, and you might wonder how they work. I mean, it's just holes on the piece of veneer with some wood behind it, for instance. But anytime you have little holes like this and the sound waves can go in there, it'll absorb the sound because of friction. The energy is dissipated by the friction as it moves through the perforated holes. It works like water flowing through a pipe, as it says here, and it works really, really well. You want to look at, basically, the better the absorption is with thinner material and smaller holes placed closer together. So you'll see some of that. You also see membrane resonators. That's for the lower frequency sounds. They're usually 12 to 16 inches deep, and they can take up a lot of room in your space. But these low frequencies, if you're having a problem with them, say in music rooms and recording studios, you need something very large to handle these big, huge waves that are coming in there. And these types of things like membrane resonators, diaphragmatic absorbers, Helmholtz resonators, they all do a good job of absorbing that low frequency sound. And where do you place all this absorbent material? Well, typically lateral over vertical, because our ears are on the side of our heads and the sound source is usually coming at us, not coming down to us. So really, that's the rule of thumb, is you place them on the walls at about ear placement, whether you're sitting or standing. That's usually 3 to 7 feet above the finished floor. But I've seen in cases where they're in the ceilings too, because the ceiling is very low and it's a very big space where the walls are really far from you. So what's the closest surface to you? It's the ceiling. So that's what's going to bounce back to you first. So I've seen people put them on the ceilings too. So again, just rules of thumb. But absorbing surfaces can only affect the sound that strikes them. They're not vacuum cleaners. These absorbers, you can't just throw them anywhere in the room and expect it's going to work great. There's a certain path that the sound travels in certain areas on the walls and the ceiling where it typically hits, and that's where you want to place these materials. You can see absorption at work. It should look beautiful as far as we're concerned. It should not take away from the aesthetics of the space. It should only add to the aesthetics and make it even more beautiful. And you can see how you can do that and make this really artwork for your ears as well as your eyes, okay? That's what we do. And we talk a lot about offices, but there's also the classrooms, healthcare, restaurants. All of these types of spaces have problems with background noise, with issues with HIPAA, privacy standards, with just overall loudness in a space for a long period of time, like in restaurants, that we really need to be concerned about all these different types of spaces and the noise that's generated in these spaces. So here's the takeaway. You can read that for yourself, but just realize that, you know, acoustical consultants usually use a combination of acoustical remedies. That's why I mentioned the A, B, C, and D. They'll often not come and say, well, you only need absorbers and you'll be fine. So you might see that absorbers is one piece of the puzzle, and then blocking is another piece, and they need to work together. But, you know, as long as you start the journey, start somewhere and start realizing that sound is very important, and it should be, you really should handle any issues that could come up, and you can if you know the right way to do it. And that's pretty much it. But I'll leave this up on the screen if you want to see this and just know this is where we get our information from.